The propulsion production process at Wärtsilä combines centuries-old craftsmanship with modern engineering excellence. Since 1834, Wärtsilä has been renowned for its reliable marine propulsion systems, and for over 2 decades, its production has thrived in China, the hub of global shipbuilding. This strategic location ensures faster delivery and unmatched value. Utilizing state-of-the-art technology and rigorous quality assurance, the facilities manufacture a range of propulsion products, including transverse and steerable thrusters, seals, bearings, and fixed and controllable pitch propellers. Established in 2004, the factory produces propellers from 0.5 to 11 meters in diameter, with over 3,000 blades manufactured. Certified quality exceeding ISO standards ensures Wärtsilä's products meet the demanding needs of high-end cruise ships and government vessels worldwide. The assembly of the 12X92DF engine, the world's most powerful Otto cycle engine, is a feat of precision engineering and collaborative effort. The process begins with component manufacturing and inspection, where critical parts like the 92 cm bore cylinder liners, pistons, and crankshafts undergo rigorous quality checks to ensure dimensional accuracy and material integrity. Following this, the crankcase and bedplate assembly takes center stage, forming the foundation of the engine. These massive structures are meticulously aligned and bolted to provide stability for the engine's operation. Next, cylinder block installation integrates the liners and cylinder heads, ensuring precise sealing and alignment to handle the high pressures and temperatures of dual-fuel operation. The crankshaft and camshaft assembly follows, with careful balancing and lubrication to guarantee smooth rotation at the low-speed operation of 80 revolutions per minute. The turbocharging and fuel delivery systems are installed, optimized for LNG as the primary fuel. Advanced control systems, sensors, and actuators are also integrated to monitor and regulate performance. Finally, the engine undergoes comprehensive testing and commissioning, validating its power output of 63,840 kilowatts and thermal efficiency of 51 to 53%. The construction of the Type 45 destroyers, including HMS Duncan, was a monumental engineering and manufacturing project, carried out primarily at BAE Systems Govan and Scottstown shipyards on the River Clyde in Glasgow, Scotland. The process began with the fabrication of large steel sections, including the 900-ton bow section, which traveled from Portsmouth to Scotland on a barge. At the Scottstown yard, the central section of the ship continued to take shape, with workers assembling massive steel boxes to form the hull. The hull was carefully constructed to precise tolerances, ensuring that each piece would fit together seamlessly during assembly. This modern method of shipbuilding, where ships are built in modular sections, replaced the traditional method of building entire ships in a single piece. More than 70% of the equipment aboard the Type 45 destroyer was completely new, including cutting-edge radar and missile systems. As the sections were assembled, Key equipment such as propulsion motors, gas turbines, and weapon systems were carefully integrated into the ship's structure. At one point, the ship's forward propulsion motors, each weighing 99 tons, were lifted into place using cranes at the yard, pushing the cranes to their limits. Throughout the build, approximately 590,000 meters of cables were installed to power the ship's systems, including communication, lighting, heating, and combat systems. The process was a complex puzzle of precision engineering, where each cable and pipe was carefully routed to its designated location. Once the hull was complete, HMS Daring was launched into the Clyde River. The launch was a momentous occasion, with the ship sliding into the water after a meticulous process that involved hydraulic jacks and drag chains. The ship was then moved to dry dock, where further outfitting and testing took place, culminating in sea trials. The construction of the Type 45 destroyer marked a leap forward in naval technology, as the vessel was designed with future advancements in mind, ensuring its relevance for years to come. The project, which took 55 months, involved over 2.3 million man-hours, with 8,000 tons of material used in the building process. It was a true collaboration across multiple locations in the UK, with sections of the ship constructed in Portsmouth, Barrow, and Rosyth before being brought to Glasgow for final assembly. Burrard, the mega transport experts, played a critical role in the loadout of the U.S. Navy's littoral combat ship, LCS, Coronado, constructed by Otto in Mobile, Alabama. This 418-foot-long, 107-foot-wide vessel, weighing 2,800 tons, required a meticulously planned and executed two-step transport process. Utilizing 104 axle lines of self-propelled modular transporters, SPMTs, Burrard smoothly transferred the Coronado from the final assembly bay to a deck barge. Following the initial rollout, the vessel was barged downriver to undergo transloading from the deck barge to a dry dock for its subsequent launch. The entire operation, completed within 2 days, showcased a significant leap in efficiency and safety. The refined rollout method not only reduced the time required but also underscored Otto's commitment to optimizing processes for future LCS deliveries. Bulgaria's ship repair and maintenance industry is a vital component of its maritime sector, leveraging the country's strategic position along the Black Sea. The industry is characterized by several key facilities and a workforce dedicated to servicing a diverse range of vessels. A prominent player in this sector is the Odesso's ship repair yard, located in Varna. Established in 1955, it stands as Bulgaria's largest and most well-equipped ship repair facility. The yard spans approximately 320,000 square meters and is capable of accommodating vessels up to 35,000 DWT for dry docking and up to 150,000 DWT for afloat repairs. As of 2015, Odesso's employed over 700 individuals and handled around 60 docking projects annually, servicing various vessel types including general cargo ships, bulk carriers, and oil tankers. The Bulgarian National Association of Shipbuilding and Ship Repair, BULNAS, serves as a central organization representing the interests of the industry. BULNAS comprises members from shipbuilding and repair yards, machinery manufacturing companies, classification societies, and research institutes. The association's mission is to promote the development and competitiveness of Bulgaria's shipbuilding and repair sector. In recent years, the industry has witnessed significant projects and investments. For instance, in August 2023, MTG Dolphin plc launched the first multi-purpose modular patrol vessel, MMPV, for the Bulgarian Navy, marking a milestone in domestic naval production. Additionally, in June 2024, the sailing ship Kaliakra underwent maintenance at Tarim Shipyard Flotsky Arsenal in Varna, highlighting the ongoing demand for repair services. The broader transport equipment repair industry in Bulgaria, which includes ship repair services, was valued at €220.1 million in 2024. This sector encompassed 675 businesses, reflecting a compound annual growth rate, CAGR, of 4.9% between 2019 and 2024. Despite this growth in the number of businesses, the market size experienced a decline at a CAGR of 12.4% over the same period, indicating challenges such as increased competition or market saturation. Looking ahead, the industry is expected to experience growth over the next 5 years. Factors contributing to this positive outlook include Bulgaria's strategic maritime location, ongoing investments in infrastructure, and a skilled workforce. However, the industry must navigate challenges such as maintaining competitiveness in the regional market and adapting to evolving environmental regulations. The manufacturing of propellers combines advanced techniques with meticulous craftsmanship. The process begins in the wax room, where wax pellets are injected into aluminum molds using high-pressure equipment. Aluminum is chosen for its thermal conductivity, ensuring rapid solidification of the wax. This wax pattern forms the foundation for subsequent steps. Next, the wax blades are welded using specialized tools and sculpted to create precise geometries. These patterns are then cleaned to remove any residues and prepared for the ceramic shell process. The wax model is repeatedly dipped in refractory slurries, alternating with coatings of silica sand, to build a robust ceramic shell. This multi-layered shell is dried to create a strong mold. The wax is removed by melting it out in an autoclave, with the recovered wax recycled for future use. The ceramic shell is then baked at 1,800 degrees Fahrenheit to strengthen it further. Molten stainless steel, heated to approximately 3,000 degrees Fahrenheit, is poured into the prepared mold. For propellers, a 15:5 stainless steel alloy is used, comprising 15% chromium and 5% nickel for strength and corrosion resistance. Once the metal solidifies, the ceramic shell is broken away, and any residual material is removed via sandblasting. The propellers are ground and polished in a multi-step process involving ceramic stones, synthetic plastics, and corncob media, achieving a mirror finish. Final geometry checks ensure adherence to specifications. The trail edge is carefully ground to optimize water holding capability. After thorough quality control inspections, any adjustments are made using mallets and anvils. The finished propellers, meeting Yamaha standards, are packaged and ready for use, ensuring reliable performance for marine applications. The repair process of the Kapal SAR KRESNA during its docking at Kodja Sabang involves several key steps to ensure the vessel's maintenance and functionality. The process begins with the docking, where the vessel is securely positioned in the dry dock for inspection and repair. This is followed by a thorough cleaning of the hull plates, focusing on the lower sections to remove any accumulated debris or marine growth. Next, welding of the hull plates is carried out to repair any structural damages. The freshwater tank is also inspected, cleaned, and repaired as necessary. Afterward, the upper hull cleaning is done to remove dirt and biofouling that may have built up. The anchor painting process is completed to prevent corrosion and wear, ensuring that the equipment remains in working condition. Special attention is given to the propeller maintenance, where the propeller is cleaned and any damage is repaired. The sea chest is cleaned to improve the flow of water and prevent blockages that could affect engine performance. The installation of aluminum anodes follows to protect the vessel from electrochemical corrosion, while the hull is coated with an orange paint for visibility and corrosion resistance. The process continues with the application of anti-fouling paint, AF, to prevent marine growth on the hull, and AC paint is applied to the waterline to protect against wear. Finally, the yellow coating, less cooning, is applied for additional protection. The wind towers industry plays a crucial role in the global renewable energy sector, driven by increasing demand for sustainable power sources. Wind towers serve as structural supports for wind turbines, housing components such as the nacelle, gearbox, and generator. These towers are typically made from tubular steel, concrete, or hybrid materials and can reach heights of up to 160 meters, depending on the wind farm's location and turbine capacity. Globally, the wind power market is growing rapidly. As of 2024, the cumulative installed wind power capacity has exceeded 1,200 gigawatts, with onshore wind farms accounting for about 85% of this total and offshore installations comprising the remaining 15%. This demand has fueled the growth of the wind tower manufacturing sector, which produces an estimated 50,000 towers annually, with Asia Pacific, Europe, and North America being the primary markets. A standard onshore wind tower is generally 80 to 120 meters in height and 3 to 5 meters in diameter, weighing between 150 to 200 tons. Offshore wind towers are larger, with heights exceeding 140 meters and weights up to 400 tons. The cost of a wind tower typically represents 20% to 25% of the total wind turbine cost. For example, a 3 megawatts wind turbine system may cost around $4 million, with the tower contributing $800,000 to $1 million to this total. Manufacturing wind towers involves several key processes, including steel plate rolling, welding, surface treatment, and quality inspection. The steel used is usually high-strength, low-alloy steel with a thickness ranging from 15 mm to 60 mm, depending on the tower section. With governments setting ambitious renewable energy targets, the wind tower industry is poised for sustained growth. For instance, the EU aims to achieve 510 gigawatts of wind power by 2030, while China targets 1,200 gigawatts of combined wind and solar capacity by the same year. This expansion will require substantial investment in tower manufacturing, transportation, and installation, further driving technological advancements in the sector. Interstate treating in Odessa, Texas, revolutionized its beam cutting process for skid fabrication by integrating the SPC 3000 vessel cutting machine. Previously, the manual process demanded over 500 hours per skid, creating bottlenecks and quality issues. The new automated system reduced this time frame to just 24 hours, achieving precision cuts and eliminating common problems such as misaligned holes and material gaps. The HGG equipment's efficiency enabled interstate treating to transition from 5 days to 1 day for beam layout, ensuring seamless production flow and improved quality control. The machinery's precision drastically reduced rework and allowed for cutting beams up to 12 inches thick with unparalleled accuracy. The investment proved its value within 14 months, consistently meeting and exceeding operational expectations. This technological advancement not only accelerated production but also positioned interstate treating as a leader in efficient skid fabrication, with a month's worth of beams now processed in just a week. The installation process of the Veja Mate offshore wind farm involved a complex and highly coordinated sequence of operations to ensure the successful deployment of 67XXL monopile foundations in the German Bight. Designed to support 6 megawatts turbines, these foundations are critical for generating enough energy to power approximately 400,000 homes in Germany. The process began with the design and fabrication of the 67XXL monopiles in Rostock, Germany. Each monopile measured up to 85 meters in length, with a diameter of 7.8 meters and a weight of up to 1,300 tons. Once fabricated, the monopiles were transported on barges via the Kiel Canal to the feeder port in Eemshaven, Netherlands, where the next phase of the operation commenced. Mobilization of the installation vessel Skyla was a key step. Equipped with a custom-designed 650-ton double-level pile gripper frame, Skyla was specially prepared to handle operations in high sea states. The upending and installation of the world's largest monopiles were executed with precision, ensuring proper placement and stability. Driving the monopiles to their target depth required advanced noise mitigation systems, including the hydro sound damper and a double big bubble curtain, to minimize environmental impact. Scour protection was installed using the fall pipe vessel rock piper to prevent erosion around the monopiles. Following this, a survey tool with laser precision was deployed to ensure accurate alignment of the top flange for the turbines. Transition pieces and subsea anode cages, transported from Aalborg, Denmark, were installed with meticulous attention to detail. The transition pieces were secured by bolting and grouting after marine growth was removed. This process ensured the structural integrity of the turbine foundations. The installation of offshore platforms involves two critical phases: jacket installation and topside installation. Jackets, the substructure of platforms, are typically installed using the launching method. In this process, the jacket is transported horizontally on a barge and launched into the sea, where it is upended and secured to the seabed using piles. Topside installation involves placing the deck structure on the installed jacket. This is usually done using heavy lift vessels like the Oceanic 5000, equipped with cranes capable of lifting up to 4,400 metric tons. The topside is lifted from a transportation barge and positioned onto the jacket with precision. The Oceanic 5000's advanced systems, including dynamic positioning, stingers for pipeline laying, and high-capacity tensioners, ensure efficient operations. The vessel's dual capabilities in structural installation and pipeline laying, combined with its ability to operate in shallow and deep waters, make it versatile for a wide range of offshore projects. Offshore platform installation is a complex operation that demands precise engineering and seamless coordination. These platforms are essential for oil and gas extraction or renewable energy systems, such as wind turbines, and are installed in various marine environments, ranging from shallow waters of 20 meters to ultra-deep waters exceeding 3,000 meters. The installation process involves several key steps. Components like topsides, jackets, or floating hulls are transported to the site using barges or transport vessels. Positioning and anchoring utilize GPS and dynamic positioning systems to achieve precise alignment within plus or minus 10 centimeters. Finally, topsides are lifted and mated with jackets or hulls, and subsea connections are completed using remotely operated vehicles. The choice of platform type, fixed or floating, depends on water depth and environmental conditions. Fixed platforms are commonly used in shallower waters, typically up to 500 meters deep. These platforms rest on jacket structures secured to the seabed with piles. For instance, the Shell Mars B platform in the Gulf of Mexico, weighing over 42,000 tons, is a testament to the engineering required for such installations. In deeper waters, floating platforms like spars, tension leg platforms, and semi-submersibles are more suitable. These structures are anchored using mooring systems or dynamic positioning and can operate in depths exceeding 1,000 meters. A notable example is the Perdido spar platform, which operates at an impressive depth of 2,450 meters. The installation process relies heavily on advanced equipment and specialized vessels. Heavy lift vessels, such as the Sleipnir, are capable of lifting modules weighing up to 20,000 tons. Pipe-laying vessels, on the other hand, are crucial for installing subsea pipelines, often achieving laying speeds of 3 to 5 kilometers per day, depending on sea conditions. The growing focus on renewable energy has also shifted attention to offshore wind platforms. At the 120-acre Mitsubishi Hitachi Power Systems Americas facility, innovations are forged every day to create the world's largest and most fuel-efficient gas turbines. These turbines are built to operate at temperatures reaching 2,900 degrees Fahrenheit and speeds of 3,600 RPM, capable of powering over 300,000 homes. With cutting-edge technologies such as robotics, 3D printing, and water jet technology, the facility houses some of the largest lathes, up to 220 tons. Highly skilled workers, experts in their fields, manufacture components like advanced combustor cooling and 3D compressor blades. The Faro Arm Coordinate Measurement Machine, CMM, is a versatile, portable 3D measurement tool used to accurately capture the geometry of gear surfaces. By using a probe attached to an articulated arm, it measures the dimensions of gear teeth, including their profiles, spacing, and angles. The data gathered allows engineers to ensure precise gear tooth fittings, improving quality control in gear manufacturing processes. The FlexScan induction scanner is a compact, affordable heat treatment system designed for hardening, tempering, annealing, brazing, and other applications. It pairs with induction power supplies and coils, offering flexibility for small and large parts. The system includes a dual spindle lift and rotate actuator, quench subsystem, and temperature management features. Optional add-ons include robotic handling, conveyors, and quality assurance systems. With modular configurations, it can be integrated into larger machine cells for enhanced automation and efficiency in heat treatment processes. Komatsu, a global leader in the construction and mining equipment industry, employs advanced manufacturing processes across its production network to ensure high quality and durable machinery. Its primary manufacturing facilities in Japan, including the Oyama and Osaka plants, are renowned for integrating automation, precision machining, and robotic assembly into their production lines. The process begins with raw material preparation, where high-grade steel is cut, formed, and machined into key components like frames, booms, and buckets. Komatsu employs state-of-the-art CNC machines for precision cutting and shaping, ensuring that components meet strict dimensional tolerances. For hydraulic excavators, one of Komatsu's top-selling products, the production process involves multiple stages. After machining, key components such as booms, arms, and undercarriages are welded using automated robotic welders to ensure uniformity and structural strength. The welding process is critical, especially for large-scale mining excavators, where structural integrity must withstand extreme operational loads. Once welded, components undergo heat treatment to enhance durability and resistance to wear. Following this, the subassemblies are painted using electrostatic coating for corrosion protection before proceeding to the final assembly line. In the final assembly stage, major components such as the engine, hydraulic system, and cab are fitted onto the machine chassis. Komatsu emphasizes precision during this stage, employing torque-controlled assembly systems to ensure proper installation of high-stress parts. Each completed machine undergoes rigorous testing, including load-bearing tests, hydraulic performance checks, and electronic system calibration. For large mining trucks, additional dynamic testing is conducted on specially designed test tracks to simulate real-world operating conditions. The production process of tungsten carbide tipped (TCT) circular saw blades involves several key stages to ensure high precision and durability. The process begins with laser processing, where the blade's shape and size are accurately cut. Next, brazing processing is performed to attach tungsten carbide tips to the blade, ensuring excellent abrasion resistance and toughness. The blades are then subjected to thorough inspection to verify their quality and consistency. After passing inspection, the blades undergo heat treatment to enhance their hardness and durability, making them suitable for cutting a variety of materials, including non-ferrous metals like aluminum and brass, as well as carbon steels. These processes are carried out with strict quality control to produce high-performance saw blades capable of delivering high cutting speeds and precision, making them ideal for use in industries requiring robust cutting tools. The production of galvanized steel elbows and round air ducts is a crucial segment of Russia's HVAC, heating, ventilation, and air conditioning, and construction industries. These components are vital for effective air distribution in residential, commercial, and industrial spaces, with applications ranging from ventilation systems to exhaust installations. Galvanized steel is preferred due to its durability, corrosion resistance, and cost-effectiveness. Russia's galvanized steel output was approximately 2.7 million tons annually as of recent data, with a significant portion utilized for ducting and air control systems. The use of galvanized steel in HVAC systems is projected to grow at a compound annual growth rate of 5%, driven by increased infrastructure and urbanization projects. A standard product in this category is the galvanized steel elbow with a thickness of 1.2 millimeters, designed for smooth airflow in duct systems. A specific example includes elbows with a diameter of 800 millimeters, a radius of 2,000 millimeters, and a 90-degree bend. These specifications are widely used in large-scale industrial and commercial applications where high airflow is required. The production process involves cutting, bending, and welding galvanized steel sheets, followed by quality checks to ensure precise dimensions and structural integrity. Manufacturers in Russia utilize advanced machinery for automated production, ensuring efficiency and uniformity. A single production line can produce up to 500 units per day, depending on complexity and size. With an emphasis on modernization, Russian manufacturers are increasingly adopting CNC machinery and laser cutting technologies, boosting both precision and production capacity. Exports of galvanized steel components, including air ducts and elbows, also contribute significantly to the industry, with neighboring countries in Eastern Europe and Central Asia being key markets. This sector's steady growth reflects Russia's broader industrial capabilities and its focus on supporting infrastructure and modernization needs. The hot dip galvanizing dipping process provides superior corrosion protection for steel components by creating a durable, metallurgically bonded coating of zinc-iron alloy on the steel surface. The process begins by thoroughly cleaning the steel to ensure optimal adhesion. Once prepared, the steel is dipped into a molten zinc bath, typically heated to around 450 degrees Celsius, 842 degrees Fahrenheit. During immersion, a metallurgical reaction occurs between the zinc and the iron in the steel, forming a series of zinc-iron alloy layers topped with a pure zinc outer layer. This zinc coating acts as a robust barrier against environmental factors such as moisture, chemicals, and air, which can cause corrosion. Additionally, the zinc layer provides cathodic protection, meaning that even if the coating is scratched or damaged, the surrounding zinc will corrode preferentially, protecting the underlying steel. The hot dip galvanizing process offers long-lasting protection with minimal maintenance, making it a cost-effective solution for steel used in harsh environments. Common applications include structural steel, piping, railings, and fasteners, where high durability and corrosion resistance are essential. The axial closed die rolling machine is a specialized metal forming equipment used for the precision production of rotationally symmetrical parts such as gears, splines, and threads. This process involves shaping metal workpieces by pressing them between two or more closed dies while the material is simultaneously rotated and rolled axially. The machine typically consists of a fixed die, a moving die, and a clamping system. The workpiece is placed between the dies, and once clamped, the machine applies axial force while rotating the dies or the workpiece. The dies, which have pre-machined cavities in the desired shape of the final product, gradually press into the workpiece as it rotates. This results in precise, high-strength parts with excellent surface finish and minimal material waste. Key benefits of axial closed die rolling include high production efficiency, minimal post-processing, and improved mechanical properties of the rolled components due to grain refinement and work hardening. Common applications of this technology include the automotive, aerospace, and energy industries, where complex, high-strength components are essential. Underwater welding of brackets for anodes is a critical process in marine engineering and offshore construction, used primarily for the cathodic protection of submerged metal structures, such as ship hulls, offshore oil rigs, and pipelines. This process involves attaching anode brackets to the structure using specialized welding techniques, ensuring durability and corrosion resistance in harsh marine environments. Welding methodology. Underwater welding for anode brackets is generally performed using wet welding or dry hyperbaric welding methods. Wet welding is more common due to its flexibility and lower cost. In this method, shielded metal arc welding (SMAW) is typically used, employing waterproof flux-coated electrodes designed for underwater applications. The most commonly used electrode is the AWSE 6013, with diameters ranging from 3.2 mm to 5.0 mm, depending on the size of the bracket and the base material thickness. The welding current for underwater SMAW typically ranges from 120A to 180A, with a direct current electrode negative (DCEN) polarity. The welding voltage ranges between 22 volts and 26 volts, depending on water depth and electrode size. Bracket specifications. The brackets used for mounting sacrificial anodes are generally made of mild steel or stainless steel, depending on the type of structure and environmental conditions. These brackets are designed to fit the specific type of anode, typically zinc or aluminum alloy anodes. A typical bracket for a zinc anode weighs around 3 to 5 kilograms and has dimensions of 300 mm by 100 mm by 10 mm. The bracket design includes mounting holes or clamps to securely hold the anode in place. For proper cathodic protection, the brackets must be spaced at specific intervals along the structure. For example, on a 40-meter-long pipeline, anodes with welded brackets might be installed every 5 meters, resulting in approximately 8 to 10 anodes per side. Key considerations. Weld integrity. Since underwater welding is performed in a high-pressure, low-visibility environment, the welds must be inspected for defects such as porosity and cracks. Non-destructive testing (NDT) methods, such as ultrasonic testing (UT), are often employed. Depth limitations. Wet welding is commonly performed at depths of up to 30 meters, beyond which the risk of weld defects increases significantly due to increased water pressure and cooling rates. Safety measures. Divers must wear specialized dry suits and welding helmets equipped with air supplies and communication systems. Ensuring diver safety during high-voltage operations underwater is paramount.